So my name is Nicole White, and first of all, who am I? So I went to LSU not too long ago, got some degrees in math and economics. Then I went to UT Austin, got a degree in statistics. Any alumni in the room? All right, nice. Yes, thank you. And now I currently work for Neo4j as a data scientist. And that last point brings up, why I think I'm qualified to talk about Cypher. We actually use Neo4j internally at Neo4j, so actually I get to write Cypher professionally all day long, which makes me very happy. And Emil mentioned earlier at the keynote, when you ask someone what they love about Neo4j, Cypher's always in the top 3. And for me, it's definitely #1, and I think also #2 and 3. So I'm a big Cypher fan. I love it so much, I answer questions on Stack Overflow for fun about Cypher. So I'm going to be talking about, for the next 40 minutes, some of my favorite things about Cypher and highlighting those things along the way. So I think Emil mentioned this, but essentially Cypher is ASCII art. You draw out the graph pattern that you want to return in your result set. And so this is a tweet, some guy, Jay. So this is the only thing he learned apparently in Neo4j training, is that you draw ASCII art to code. So that's pretty much what Cypher brings to the table. Who here has coded Cypher, has written Cypher queries? Who here has never seen a Cypher query in their life aside from what they saw like on the keynote? Okay, excellent. Okay, so like I said, you draw the graph patterns. So for nodes, you draw open and closed parentheses to represent a node, kind of drawing a circle, if you will. And then for relationships, it's open, closed, square brackets to draw that kind of edge style thing. And then to specify a pattern, you're going to use hyphens in combination with these nodes and relationships. So if you wanted to find node relationship node, you do these parentheses, hyphen, and then open close square brackets, and then another node on the other side, because nodes are connected by relationships. And so that's how you specify something like that in Cypher. And then optionally, actually this is probably how you'd use Cypher most commonly, is you'd specify a direction of the relationship, because in Neo4j, relationships are necessarily directed. So you would do that with greater than or less than signs, right? So here we're saying that this node on the left has an outgoing relationship to this node on the right, and then vice versa there on the bottom. So that's the shell of what we're doing in Cypher. That's the template, I suppose. And eventually we'll fill this in with what kind of nodes are we wanting to traverse, what kinds of relationships are we willing to traverse, and we'll specify that in the Cypher query as we get into that. So I have an example data set for us today to learn Cypher together. Who here knows what Starcraft is? Okay, I thought this was risky. I was like, I hope at least one person knows what Starcraft is. But luckily you guys are just as nerdy as I am, so that's good. If you don't know what Starcraft is, that's totally fine. It's not necessary to understand what's going on. Essentially, you have units in buildings, and they have requirements, right? So there's a tech tree. This building requires this building. So you can't build this until this exists. And so there's this big tech tree. So if you wanted to build, for example, a barracks, you have to have a command center. So there's this hierarchical tree of requirements for both units and buildings, right? And conveniently, Neo4j is very good at storing, modeling, and querying tree-like structures. So I imported just the Terran tech tree into Terran's one of the things in Starcraft, into Neo4j so that we can learn Cypher together with this data set. So hopefully this is somewhat visible. We just have two node labels going on here in this example data set. We have buildings and units. And then we have the hierarchy of requirements modeled with a requires relationship. So here, for example, we have that the factory here in the middle, this blue factory node, is a building that requires a barracks, and then the barracks requires a supply depot. So there's this big hierarchy of building requirements down to the lowest node, which is usually the supply depot or not shown here, command center. And then we also have units that have requirements. So we can see the medevac requires a starport requires a factory. So there's these required relationships between both buildings and units. You know, what needs to exist before we can build this thing. So we have that. And then we also have builds relationship, saying this building builds this unit. So the barracks builds these 4 units, Marine, Marauder, Ghost, Reaper. It's a Starcraft 2, by the way. Some of you older folks might not be familiar with these terms, but it's roughly similar. So yeah, we have requires relationships and builds relationships to capture just that part of the world we're exploring today in Cypher. And then finally, I wanted to touch on the properties we have on these nodes so that we're all on the same page when we start looking at Cypher queries together. It costs money to build these things in this game, minerals and gas. So we have properties. We have the name of the thing, either the unit or building has a name property, and then how many minerals it costs to build it and how much gas it costs to build it. So just a cost for building that thing. And we'll be using these properties in some of the queries. So let's look at our first Cypher query together by answering the question, which units can be built at the barracks? So we saw visually earlier the answer to this. But let's look at the Cypher query that can answer this question for us. So this is our first Cypher query. So I guess the most important thing is the match clause. This is where you draw, like I said earlier, you draw out the graph pattern that you're interested in retrieving. So remember I said you put nodes in parentheses? Well, here we're saying we want to start at a building labeled node, and we specify that with a colon. So anytime you see a colon something, it's saying I want this type of entity. So here on the left, we're saying we want a building type node, a node with a building label, rather, is probably the correct way to say it, that has an outgoing relationship of type builds to a unit node. And then we have these things called identifiers preceding those colons. They're just variables. They can be whatever you want. I could have done ABC, XYZ. It's just a matter of preference. And so those entities are now bound to those identifiers or variables. And then you can use those variables in the following clauses, like where and return. So here, we're matching on building builds unit. We've assigned identifiers, and then we're saying where the name property of that building node has to be barracks. So this is just a classic where clause. I'm sure most of you are familiar with that from SQL. And then we're referring to those variables in the return clause. We're returning all of those entities, right? So that is a pretty standard query match where return, where we specify the graph pattern that we're interested in, filtering based on a property on one of those entities, and then returning results. So this is, if we were in the Neo4j browser, this is what we would get. We actually returned the entities themselves, so the result is visual. So it actually shows us a visual result of our data. So we have the barracks, and then we have all the units that can be built at that building. Okay, so what is the average cost of units at each building? So intuitively, you'll probably think, oh, we're going to need a group by for this. But there's no group by in Cypher. It's inferred from your return clause or with clause. So here we have the same match clause, we're matching on a building with outgoing builds relationships to a unit. Notice we've left off the identifier on that builds relationship. We don't need it, so there's no sense in binding it to an identifier. But we do need the building and the unit bound because we're going to use that in the return clause. So we've bound the buildings to B, the units to U, and then we're returning the name of the building because properties are accessed with identifier.key. So remember, there's a name property on all of these things, and you access those values with identifier.key. So we're returning the name of the building, and then the average of all the units that can be built at that building, the average minerals, and then the average gas. Because minerals and gas, as you recall, are properties on those units for how much they cost to build. So this is, for each building, giving us the average mineral and gas cost. And you don't have to explicitly say, I want to group by this. It's essentially inferred from your return clause. Yeah?
You mean each building or each building type?
The question is each building or each building type. I'm not sure what building type is. There's not a type of building. This is for each building. So this is the average cost of units at each building. So each building has a number of units, right? Greater than 1. And so this is for each building as showing the average for all those units. And so these are all of our buildings that can possibly build something, and the average mineral and gas count. So if there are any buildings that don't build units, which there are, they are not included in this result set because they don't match on this query. So the match clause is what I like to say, or I explain it as being all or nothing. It's not as if it's starting up building nodes and then figuring out which have builds relationships. It's only finding buildings that have those builds relationships outgoing to a unit node. So if there are any buildings that don't build any units at all, they're just support buildings or something, they aren't returned in this query. They don't have an average of 0 or anything. They're just not there. So the match clause is what I like to call all or nothing.
So B name presumed to be unique, right? Can we duplicate B names?
So the question is B name unique? In this case, it is. The name property is unique per building. That doesn't need to be the case. You can have multiple buildings with the same name. It won't stop you from doing that unless you have a uniqueness constraint on that property. Neo4j supports uniqueness constraints. So I can create a constraint on this saying buildings have to be unique by the name property. And then if I tried to add another building that had the same name, it would reject the transaction. But you can technically have multiple nodes with duplicate properties.
So in your example, you got more than one factory?
In my example, do I have more than one factory? No. So all the buildings and units are all unique by name in this particular data set. You had a question?
We assume that the building will separate. And no two buildings will the same building.
Sorry, say that again?
And no two buildings building the same building.
That's correct. The question is, are there two buildings building the same unit? No. Units can only be built at one building. Yeah. Sorry, I'm going to have to move on. We can circle back, though. So what does the engineering bay immediately unlock? And by that I mean, once you build the engineering bay, what can you now build as a result of doing that? So all we need to do there is traverse that requires relationship up one more level from the engineering bay. So here we're matching on a building and traversing its outgoing requires relationship, where the name of that top building is the engineering bay. So these are the buildings that, once the engineering bay is built, you can now build that building. And so that's done by just traversing one level, one step of that requires relationship. So here, in the previous queries, we were matching on buildings building units. Now we're matching on buildings requiring other buildings because we have requires relationships between both buildings and units in buildings. So here on the both left and right, we're using the building label. And then we're saying that the name of this node has to be engineering bay. And then we're returning all of that in the return clause. We're returning the entire pattern. And visually, that'll give us something like this. So here's our engineering bay, and then in the middle, and then we have all these buildings. These are the immediate one-step out buildings that are unlocked once you build that building. Someone? Yeah.
What if you wanted to see what does the engineering bay immediately unlock, not what buildings the engineering bay. So if you also wanted to know what units this unlocks, what was the query?
So I think the question is, what you want to also know what units at the same time. So there's a few ways you can do that. Actually, I'm afraid to Alt-Tab, because I'm not sure what will happen. That wasn't so bad. I have it mirrored, but I can't see it on mine. This is going to be a disaster because I can't see it on mine. We'll do that at the end. How about that? But I do like writing Cypher live, but I'll do that later. Right, so those are the, but yes, I mean, to answer the question, yeah, it'd be very easy to also write a query, which buildings and units does the engineering bay unlock? That's an easy query to write. So which buildings have no dependencies? No dependencies. Which buildings can we build right away without having anything else on the map? So to do something like that, you can use a pattern in the where clause itself, which is quite nice a lot of times. So here we're matching on buildings. So our match clause is just matching on the building label. It's not specifying any relationships. And then we're saying that this pattern cannot exist. So where not? So we're trying to get buildings that don't have any incoming requires relationships, or outgoing requires relationships, sorry. So buildings that don't require anything. So they're at the bottom of this, or I guess the top, depending on how you think of it, of this tech tree. So we're using a where clause and specifying that this pattern cannot exist to the building, and then we're returning buildings that fit that criteria. There's actually a new way to do this with a new query or Cypher keyword size that checks the degree of nodes, which I can show later. You can essentially check that the degree of the node is 0, so meaning that there's no relationships attached to it, which, again, I can show later. So there are...
Size keyword, I couldn't find it in Cypher reference doc. I was looking into that.
Yeah, size is like really secret right now, apparently. I think it's in 2.2, but it's not in the docs or the ref card. So I should definitely show it later because it's so useful, but not in the documentation. So these are 3 buildings that do not have any requires relationships attached to them. So we have the refinery, the command center, and the supply depot. These are buildings that you can build from the start of the game without anything on the map. Okay, which units have additional requirements beyond their builder? So we have both the builds relationship in there and the requires relationship. Most units simply require the building that they're built at, but some have additional dependencies that circle around that building, around that building, and are not built at the building that they most immediately require. So to get something like that, we'll need a couple lines here in our match clause. So you can specify, of course, multiple patterns in your match clause, and whether or not you comma separate and bring it down to a new line is a matter of preference. I could have put this all in one line, but that doesn't look very good on a slide. So you can use commas to keep your query from going off several characters down horizontally in your code. So yeah, it's just a matter of preference, no performance difference. I usually like to do left to right, comma, left to right, just to keep things readable. But anyway, so here we're on which units have additional requirements beyond where they're built, essentially. So here we're finding the building that the unit is built at by matching on the building that builds the unit. And then we're also getting the first most requirement of that unit. So here, up in this first line of the match clause, we've bound that unit node to U. And then down here in the second line of this match clause, we're using that same identifier U. So this is referring to the same node as up here. It's just being extended down to the second line. So pretend this is just one big line, if you will. So we're matching on the building that builds the unit and then getting the first most requirement of this unit, another building where that other building is not the same. So these, that's how you specify in the where clause that two things are not equal, is the less than, greater than signs together like that. So I'm saying this other building cannot be the same as the building that built it. And then we're returning all of that information.
I think you should be able to skip this where clause.
You can't, because there are buildings that are, so I'm trying to get away from the buildings that are built at the same place.
Yes, but I think much query, same clause pretty much only once.
I know what you're saying. In this particular example, you need the where clause because there are buildings that are built at the same place at which their immediate requirement is.
The way Cypher, I think, works, my experience with it, is that one node will only be matched once.
That's absolutely correct, but these are different relationship types. There's actually, both these relationships exist between the nodes, so I have to filter. I can show that, add that to my list of things to show at the end. Trust me, it's you need that where clause because there are cases where those two nodes are the same. Other and builder are the same node, and I want to filter that out. So this is what it's finding. It's finding units that are built at a building, but their most immediate requirement is something else. So like the battle cruiser, for example, is built at the starport, but it requires, its most immediate requirement is something else. It's the fusion core. If this might help, all the other units that were omitted from this query, their requires relationship was right back to the same building they were built at. And so that was being filtered out in that where clause.
So that's an implicit and statement in your query,
So the question is that an implicit and? Yeah. So this is saying this relationship exists and this relationship exists. You can do or as well. Add that to my list of things to show at the end. You use like a pipe, essentially. Actually, it won't work in this data set very well, but I can show it. Okay. What's the most expensive unit that can be built at the factory? Here, I just wanted to show some ordering and limiting, because that's a pretty common way to use Cypher, is to order and limit your results. So match clause is pretty standard here. We've seen this a few times already. Building builds unit, where the name of the building is factory, and we want to return the name of the unit. So we're returning the name property from u.name to refer to that unit node, how many minerals it takes, how much gas it takes, and then we're ordering by the total cost descending limit 1. So hopefully that you can use order and limit right after your return clause like this. It's actually pretty flexible. You can use it before, assuming you have a with clause in there, which I haven't covered yet. But yeah, so we've returned the name, the minerals, the gas, and then anything that's still in the, I guess, namespace within the scope of the query, you can use with order and limit. So U is, of course, still in the namespace of the query. We haven't actually done anything to the namespace. And then we can order by that sum descending and just keep the top one. So limit 1 is going to find the most expensive unit that can be built at this particular building, the factory, and that is the Thor. It costs 300 minerals and 200 gas, and that's its name, and that's what it looks like. Any questions with order and limit? Yeah?
Does Cypher has a concept of stored procedures, or rather the concept?
Question was on stored procedures. That was covered at the keynote. So I will refer you to that. It's coming soon in 3.0, but not right now, no. Okay, now we're getting into the good stuff. What does the barracks unlock up to 2 levels deep? So this is a variable length question. So it could be, I want both 1 level deep and 2 levels deep. Well, it's quite easy to express in Cypher with variable length path matching. So here, or previously, we've just been matching on length 1 relationships, just one step of them. But you can specify, I want up to 2 of these, and you do that with min.max after the asterisk on the relationship type. So within these square brackets, after the relationship type, you say asterisk, and then the default minimum is 1, so I've omitted it here, but the default is 1. You can specify it if you want, and then .max. So this is saying I'm traversing up to 2 steps out from this node, where the name of the building over here is barracks. So we're getting what the barracks unlocks up to 2 levels deep at this point. And I don't think I've done this yet, but previously I've been binding everything to nodes and relationships in terms of the identifiers, but you can actually assign entire paths to an identifier. So here we have match p equals. That's binding that entire pattern or entire path to an identifier p, a variable p. So, and then I'm returning that entire thing in the return clause. So it's a nice way to avoid having to bind literally everything in your match clause to separate identifiers. You can just bind the entire thing to one variable. And this is the result. So here on, in the middle, leftish, is the barracks. And we see that we found what it immediately unlocks. So all the step 1. So it unlocks the bunker, all these other things. And then it also found stuff that's 2 steps away. So the barracks unlocks the factory, and then the factory unlocks the starport. So we found both 1 step and 2 steps away from that node by using the variable length path matching available in Cypher that you can specify within the relationships in the match clause. Okay, what are all the dependencies of a starport? So we just want to go all the way down the tree from this node. So you can do that with just by omitting the maximum on the relationship. So same thing here. We're starting at the starport, and then we're traversing the requires relationship, however far it'll go, down through the buildings, and where the name of the building is starport, and we're returning the entire pattern. Yeah, I'm going to get to that. So this is not a good query. Don't ever write this query. It's super expensive because it's an exhaustive search through that relationship type. And it's, but the next example is showing you a better way to do it. So this, the query did exactly what I explained. It traversed the requires relationship down until it no longer had anywhere to go. So starport requires the factory requires the barracks requires the supply depot, and then, as we learned earlier, the supply depot didn't have any dependencies. Remember that query earlier where we checked which buildings don't have any dependencies, so it stopped at that point, and this is the path, the only path returned from this query. But yeah, that's not a great way to write that query, so let's look at a better query, but with the battle cruiser as an example. So what's everything we need to build a battle cruiser? Well, here we're actually going to use shortest path, which is obviously much faster than an exhaustive search of every length of path. So Cypher has built in a shortest path function that you can pass a start node and an end node, and you specify you can specify the relationship type in there. So the syntax within the shortest path function is the same thing that you've been doing with the match clause already, except you just wrap it in shortest path, and I'm assigning that entire thing to P, so match P equals the shortest path between these, and then I'm saying that the unit we're starting at is battlecruiser, and I want the end node to be one of those nodes that doesn't have any requirements. So I'm going to go all the way to the bottom of the tree. So again, where the name of the unit is battlecruiser, and then we're traversing that requires relationship down to a building node, where this building node on the right side is anchored to those few nodes that don't have any dependencies. So this is obviously a much more performant query than the previous one where we did with the start port. And then we can return the entire path here. And here we got our battlecruiser, requires the fusion core, requires a start port, all the way down to the supply depot, again, which was one of the buildings that didn't have any further requirements. And so that's a much more performant query because we anchored it at both a start node and end node, and then use shortest path. Yes? Do I have? No, I don't. You should ask the tuning cipher people, which is the next talk. I will offload that question to them. Let me continue. What's everything we need to build a battlecruiser, and how much does it cost? So this is a pretty fun query. Same thing here. The match and where are the same thing from the previous slide, except now we actually want to look at some properties of all the nodes along the way. There's a few ways to do this. I personally like unwind, which will essentially take what you have wound up in a path and unwind it into individual rows. Hopefully that made a little bit of sense. We're unwinding the nodes in that path, so we're only grabbing the nodes, because the path consists of both nodes and relationships. And so there's a nodes function in Cypher to just grab the nodes out of a path. And then we're unwinding those into their own separate rows, and then returning the name, the minerals, and the gas. So basically taking the visuals that we just had in the previous, and we're getting a table of all of the things that we need and how much they cost in terms of minerals and gas. So as we saw visually earlier, we have to start with the supply depot, then we go to the barracks, then eventually all the way down to battlecruiser. And then, so these are all the stages, and these are all the two properties that or the three properties that we returned from all the nodes that were on that shortest path. Unwind does not drop relationships. It's because I unwound only the nodes in that path. So I passed the identifier P to nodes, and that only grabbed the nodes out of the path, and it dropped the relationships. Unwind is independent of that. And then finally, I wanted to show an example of using multiple match clauses. What's everything we need to build a battlecruiser, and where's it built? This isn't the only way to do the query, but I wanted to show multiple match clauses. Nothing's stopping you from doing match where, over and over to eventually get to where you want to be. So again, the match and where, the first two lines are identical to what we've just seen. But then after we find the shortest path, we then match on the building that builds the unit. So we're still using that U identifier that was bound up on the first line. So we bound the unit to an identifier U, and then we're using that again down here on the third line, and matching on which building builds that unit and returning it as a visual result. And that's what we get there. Because the previous visual result, it just had the requirements, snaking down to the supply depot, but now we also see that the start port builds the battlecruiser, and so that's how you can use multiple match clauses within a query. Okay, so with the few minutes I have left, I want to do all the things I said I would, though I don't know how with PowerPoint. Okay, excellent. So what was the first one? Something about or with relationship types. You can absolutely do that. You can do it with the pipe. So like this. So if you want to say, I want to match on nodes that builds or has a builds or requires relationship between them, this is how you do or with relations. And then if you want to do and, well, that's just your classic match clause. That's where you specify multiple patterns in the match clause. But this is how you do or with relationship types.
What about or between two matches? Builds or requires.
Well, if you want builds or requires, this is the way to do it. Maybe I don't understand. And then I want to prove someone wrong. Who was that? Sorry, I'm being mean. Is it already there? Oh. Okay, so this gives us the buildings where or the units rather, where, like I said, their builds relationship is coming from a different node than the building that is their most immediate requirement, right? But most of the units are built at the same building that is their most immediate requirement. So if I omit this, I'm also getting all of that, right? So this guy, or the Hellion, for example, the factory builds it, and it's also its most immediate requirement. So by not including where this node is different from that node, that's all included. But I wanted to filter that out. What else did we have? Size. Sorry, I got to cut you off there. Size is, what was the query I did? This one. So this was find buildings that don't have any incoming requires relationships. Or outgoing, I keep saying it wrong. So these are all buildings that don't have any outgoing requires relationships. But you can also do, as of somewhat recently, you can do size be requires. And I can specify the label, actually. So this is saying where the size of this, or the degree of this pattern, I should probably say that it's 0. And that's the same result, right? And then maybe the tuning cipher, I'm sure this is, I think this is faster, because it's just checking the degree of the node. Whereas, actually the tuning cipher people can probably answer that better. But this is, we're getting the same result here. We're getting nodes that don't have any requires relationships outgoing, except we're just checking that that pattern size is 0. It's the degree of, well, it's the size of, it's counting how many times that's happened, essentially. It's counting how many of those paths exist from that node to another node. It's the degree, I guess. I have 10 seconds, so yeah.
How do you tell how many requirements
How do you tell how many requirements you traversed? So if I want to know everything that's from the top down and how far they are from the top?
Yeah, so question is, well, you guys heard it. I'm trained to always repeat the question. How do you know how many, so like if you do something like this, how do you know how long it is? That's a good question. So we can assign the entire path to an identifier. What did I do here? I probably don't need that. So I think I did it for the star port earlier. So if I can return the P, we get that. Or you can return the length of that. And it's actually not a good example because this query is finding all paths of any length. So it found both the first, second, third paths. But essentially, the answer is to use length with the path. Probably. Not sure that really makes sense. Yeah, no. Yeah, length. I think am I good? Okay.
So I just want to find out entire network that is crossing across a node. So you showed an exhaustive relationship with the requires relationship. I want to find out, I don't want to limit myself to a relationship, but I want to find all the nodes all the relationships that pass through a node. So what's the best way to do that?
So if you can isolate it down to a single node, you can just leave the relationship type off. So let's say you want to know all of the relationships that are attached to the CSSCV node. And then you can just leave the relationship type off. Oh, by the way, that's shorthand where conditioning. I didn't cover that. I was using the where clause because I like it better, but you can also specify conditionals within the node itself with curly braces. So I can say that the name of this has to be this string. You can do that actually within the match clause if that's what you prefer. I think it looks kind of weird, so I don't do it. But that is a matter of preference. And there's no performance difference between doing it in the where clause or doing it within the match clause within curly braces. Anyway, so I can just leave the relationship type off completely. And then I could just return the type of our, actually I can return distinct, because, so here we see that it has both requires and builds attached to it. So but that would be a super expensive query if you didn't isolate it down to a handful of nodes. I mean, if you're, not omitting the relationship type is probably not a good idea unless you have a specific case in mind and you have a specific node. Yeah. Guy from what? First tweet? Oh, that's great. Oh, that's perfect. So the guy, the tweet I showed at the very beginning, he's right here. Yay! I'm going to end it on that note. That's good.